Okay, hello again, and this is another Warwick RSE video about all things programming and code. And the title of this one is loosely function design, and the sort of subtitle will be something about functions, their naming, and how you write code that has to make decisions in the sense of you generate some data and you do something with it, and at some point you can think of what you're doing as making a choice based on that data. So I wrote a blog post a little while ago about the names of functions and emphasizing that function names are supposed to make things clear to a reader of the code, and how the idea of a good function name is to reduce your mental effort by letting you substitute the entire body of a function, everything it does, for just its name, and trusting that its name accurately reflects what it does. And as we sort of said here, and to reiterate that, that's a really good analogue for the idea of a function having a single responsibility. And class is also single responsibility. If you can give them a name and a doc string, a documentation that tells you what they're for, what they do, then you've probably nailed down some sort of task for them. So we can say really quite strongly that if you have a function and you cannot give it a clear, descriptive, short name, it's bad. It does too much. It's probably not a good function, and that almost entirely holds. Now sometimes, even if it's bad, we can fairly say that it might be the best you can do, but we'll ignore that for now. We'll just say those functions are bad. They don't do one thing, and we want them to do one thing. The converse doesn't quite hold. Just because we can give something a good name, it's not necessarily true that our name hasn't, for instance, introduced a lot of context, brought in a lot of jargon, or assumed some knowledge that still means the function is being allowed to do too much because parts of the name are similarly doing too much. For instance, you could write a function called implement the entire algorithm from Jones et al., and that would entirely describe what the function does, but it's pretty clear that it's not actually a good name, and it's probably not a good function because it's doing a lot, potentially. So in our phrasing there, we've gone a bit meta. We say if a function name brings in too much jargon or context, it's probably a bad function, and we've then just put a lot of responsibility on the phrasing too much. How much is too much? I don't know. We've just pushed that question down the line a bit. Regardless, give functions good names. If you can't give your function a good name, consider, is it actually a good function, or should you make it better? And remember, the aim of your naming is to ease your mental effort. Programming's not easy. Understanding code isn't easy. So the better names you can give, the more you can be allowed to understand the program piecewise, because you understand a function and then you just substitute the entirety of it for its name. Repeating myself, but that really is the crux. You plug the functions together into a bigger program, and you don't have to keep all the details in mind at once, because you can look at things on a variety of levels, the individual lines of code level versus the bigger picture of the code as a whole level. Now, just to be clear, you don't need functions in order to produce readable, understandable code, because there exist programs, particularly short scripts, where all you need is to just break things up in concept. You have something that's just so linear, it just does a sequence of steps one after the other, that all you need is some carefully placed comments, and you've got this division of understanding just as well as if you'd written functions. That saves time, that can actually be more understandable. So don't go mad adding functions just because they're supposed to be good. They can make things worse, but that is the same concept of separating responsibilities, simplifying the complexity of something into a less complex sequence of steps. Same thing, different syntax. You're not using functions, you're using comments, maybe block scope if you're in a language that allows that, things like that. So let's just look at one kind of program and think about it in a couple of different ways. So a simple data processing program. So this was something that just came to me as a question, and I thought, I think I know the answer using maths, but I'm going to actually write a bit of program just to verify that my answer is okay, because I'm not entirely convinced by my own logic. And that's the question of, if I go out and run a 10-kilometer race at a 10 kilometers an hour pace, have I definitely during that run a 5-kilometer race at equal or better than that 10-kilometer overall pace? If I'm writing down my personal bests, can I be sure that I also did the shorter one? And is that true for half my total distance? Is it true for like less than that? Did I do a 3k at 10 kph? Did I definitely within that manage an 8k race at 10 kph? And what's the answer to that? Now, I think I know the answer from maths, and I think that the answer is anything less than half the distance, you can make that guarantee. And the reason is, for half, if you just divide it in half, if you were below the pace in the first half, then you must have been above the pace in the second half in order that the average come out good. Let's ignore nuances of time versus distance averaging, or just do whichever one makes this work. So yeah, if my first half was too slow, my second half must have been faster, and therefore one of the two halves was at more than the average, more equal or better than the average pace. Fine. For a longer distance, it's not true. I could, for instance, start really fast, meander about in the middle and finish really fast, and not be able to find a continuous bout of the average pace for, say, 8 kilometers, I think, and my program does reinforce me on this. And for anything less than half, it's also true, I think, but I don't really have the logic to explain it. It just seems unreasonable that a half would be special that way. Seems like it's going to be a change from true to not true rather than nuanced. I do have a maths physics degree, and I'm probably making somebody regret giving it to me by that little bit of logic. So, because sometimes you can just get yourself in a tangle with logic, things like the Monty Hall problem come to mind, it's nice just to write a quick program, just to run a whole bunch of trials and give me a yes-no answer to that question. And if I get, on the whole, reinforcing what my logic was, then I'm happy that I probably had a proper argument. So what I'm going to do is write a bit of program to run a whole bunch of trials of generate a list of random instantaneous paces to cover this long distance, and check that somewhere in there is a bout of at least half the distance during which I've achieved my best pace, and that is better than the average pace. Okay, so that's a really simple program. I could write a monolithic code to do that, it would be fine. But actually, when you start to think about this, you realise that while it's a very small, simple sequence of programmatic steps, if you're not careful, through the middle, you can end up with quite a lot of data. So we've got 3 inputs. We've got the total number of points we're going to run. We've got the fraction of the total distance that we're investigating this time, say a half for my original question. And we've got the number of trials we want to run in order to get this logical answer, in order to get a statistically decent answer to our yes-no question. So if we were to go at this really quite blindly, in the middle of our program, we could have up to number of trials times number of points, time points call it, times number of time points again, because we have to take each starting time and produce the list of the sub-list from that time for a length of this reduced distance that we want. So we'd have the list going from point 1 to point 50, say if we have 100 total points, we'd have the list going from point 2 to point 51, point 3 to point 52. I don't know what language you're in, so I can't remember if it's 0 or 1 based. I'm going to use Python for the whole thing, so obviously that should have started at 0. And that's a lot of data. By the way, I skipped over the fractions in that, but we have up to basically n squared times n trials data in the middle of our program. And what we want out is one thing, which is just yes or no. So we start with 3 numbers, we end up with this practically cubic thing in the middle, and we end with 1 number. So obviously that's mad. That would not be how you would write this program. You almost certainly don't ever need to have every single bit of that data in your hands at once, because that's not, well, that's just not sensible. It just feels wrong to do that, and probably, you're instinctually feeling that, yeah, you wouldn't do that. You wouldn't keep the data around for each statistical trial, because all you need to know is whether that trial succeeded or failed. Why would you keep it all around? You just distill it into a sub-answer at each point. That's the conclusion, so well done. You can probably stop listening because you've already got it. But let's look at the program if we did write it in the mad way of having all the data around. And because I'm not actually insane, I'm going to skip over the statistical trials bit. I'm going to assume that we realise from the start that we don't want to create the data for all the trials and then analyse it all. We're going to do them one at a time. So here is a program I wrote earlier. Just go through it a bit at a time. So it's Python, so it's probably best that we skip to the end and see what actually happens in terms of running the program. Okay, if we run this as a script, it's just going to call a main function, skip up to our main function. Here it is. So this is a program to answer the question that I have already described. I've made a few simplifications. I'm going to do just random numbers for this pace idea, rather than do anything with them being correlated to each other. It really ought to be the case that if it holds for random, it'll hold for correlated data in this case. I'm going to ignore time average versus distance average. I'm just going to do an average of the points, and I'm going to assume that that is then matches however I'm choosing to phrase this question. I'm going to discretize it. I'm going to use averages instead of properly integrating, because this is just a rough and ready trial. And I'm going to think about the shorter distance that I'm discussing in terms of a fraction of the total number of points. So I said 3 inputs, here they are. I'm going to have n, which is the number of time points. So that's the number of instantaneous paces I'm going to look at to get my average pace. I'm going to have the number of statistical trials I want to do. Doing 1,000, that seems like a reasonable number to give me a decent statistical yes-no answer. And I'm going to say, all right, what sub-distance am I looking for? What fraction of the total distance am I looking at the pace for? And in this case, a half, because that's the one that I'm pretty sure is the difference between yes and no. So I've got a little bit more here. I've got how often I'm going to print to the screen. That's technically an input, but it's not an input to our algorithm. And this is my output. This is going to be the number of times in my 1,000 trials that my assumption is violated, and my expectation that there is this subsection of greater than or equal to the average pace does not hold, and my trial has failed to support my hypothesis. So in this case, all I want to do is, for the number of trials I want to do, print something to the screen to be helpful, and otherwise run the trial. And if it says, no, this trial failed, add that to the failures. And honestly, I've put a comment here. What comment can I really put there that says more than the code does? It's pretty obvious that well, do things. All right, that's a terrible function name. I'm illustrating good function names. That's basically do the whole program, and that's because this is the version of the code that isn't very good, remember? But what comment can I put there that isn't just run the trials? It's the same as the function name. I haven't got much to add. After I run it, I'm going to report. I'm going to see were there any fails, and if so, in this case, I'm going to actually give the count. But equally, I could just do the is fails greater than 0. If so, print fails. Okay. So the bulk of my code is behind this function, do things. Let's find that and have a look. Remember, this isn't very good code, and this is not well commented, and this is not terribly Pythonic or any of those things. This is just code that represents a way of tackling this problem. So here is our function. It takes 2 arguments. The total number of points we should use, and the fraction of them to consider. So remember, we were talking about, in a 10k race, do I get a 5k race? That means the total number of points is whatever we want to get good statistics. I went with 500, that seemed to work for me. And that distance is going to be 0.5. So this code creates an empty list for the instantaneous pacing I'm using. Fills it in with random numbers. Those are random numbers between 0 and 1. Then it works out basically how do we fit this smaller chunk into that full list. So there's going to be the size of the smaller chunk. We have to multiply the fraction by the total number of points. And then there's going to be the range, the range over which we can fit that into the bigger list. We're going to start at 0. We're going to run that many points. So how many of those can we create before we'll run off the end of the list? And then we're going to create the giant data set of all of those sublists. And we're actually, in this case, going to create them. We're going to make copies of the subsections. Now, again, not good code. I haven't bothered to consider how this might affect my data. I haven't bothered to consider that I'm using lists, which isn't going to be the fastest. None of that matters. So here I go for a loop, and here I create the list of lists of length subsize such that I have one list for each possible starting point within my main list. This is all of the sublists of size subsize. And that's what I want to process. So get the overall average pace, the mean of my instantaneous paces. Hopefully that's going to be somewhere around 0.5. And then do the thing. This program doesn't actually look that bad until you get to this line. It's doing what you think one way of approaching the problem. You're creating all of effectively the 5-kilometer races that can be fitted into your 10-kilometer race, and now you're going to go and calculate all of their paces and check them against the average and check if there's at least one of those which was true. Yep, check there was at least one sublist which was better than or equal to the average. Actually, I've got just better than, so I should probably change that to equals. Yeah, so nothing wrong with it, but this line is packing in a heck of a lot of logic. It's not that one-liners don't have their place, but in this case, effectively the only comment I could put on that line is do the thing. It's got in, that's a decision. It's got a list. That list is being filled using a list comprehension, and there's a comparison. So that's at least 3, probably more, bits of information, because we've also got the sub-bits that are needed to make that whole thing work. That is a chunky line. And we've just kind of gone blam, make all the data and then do the thing. And this is simple code, so it really isn't that bad, but it still means that we've got this one line in our code where the entire context of our question has to still be in our mind, and that is bad. It's also risky. Imagine we wanted to debug this. Imagine we were asking ourselves, oh, have I got an off by 1 error? Have I got some minor error? I should look at the means for the subsections. Well, I can't extract them from here. I'd have to break this line up into smaller pieces. I'd have to rewrite it. And if I'm trying to debug something, starting by rewriting the bit of code I'm trying to debug is, well, never debug what is not the actual code. You might think that you've definitely rewritten it just the same way. Probably most of the time you will have, but the few times you haven't, the few times the implication changes, you will end up tearing your hair out because you can't understand what's different about the line you started with and the line you're now looking at, and you've got a bug that's just not making sense. It's a bad thing. Don't do it. So how have we ended up with code that's bad? Well, we've broken up our problem in a very strange way because that data flow has gone a bit wonky here. The flow of data through this program is basically expand, 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 blam, contract. What we'd rather have, what makes much more sense as a program, is more like expand a bit, contract a bit. Create some data, answer a question. Create some data, answer a question with it. We don't have this whole just divergence of more data, more data, more data, the answer. So just to clarify that, what do I mean? Well, to start with, we have 2 data items. On this line, we create n data items. We make a couple more here, but we're still just n and a bit, proportional to n anyway. And then on this line, we've now expanded into something proportional to n squared. Then we create one more single piece, and then this line, we never use any of our n squared pieces again after this line. We've contracted them down to a single answer, single thing, true or false. And that is kind of weird. And again, this is a somewhat trivial program. It's not very complicated. There's no branching, there's no forking, there's nothing really hard about it. But you can still see that our data, it's weird. We really have allowed our problem to boil down to one line. So let's try and think about what we should have done, what would have kept our data flow looking a bit more normal and a bit more in terms of create some data and answer something with it, and splitting up our problem into parts of data processing. So what is this line doing? It's saying is true in this list, never mind what the list is yet. So really it's just saying, well, is true in the list? Okay. Is there at least one thing for which that whole expression is true? Okay, what's that expression? Well, that expression is the mean of whatever S is at least the average pace. Okay, and what's S? Well, S is each of those sub lists of data, each of those data items that we created. So let's think about, well, what that means. We never needed to have all of those sublists. That all sub pace variable was completely, we don't need it. We could have gone straight to the mean. All we need from that is its mean. So why did we create all of that data, all of those lists, when we could just have created one number per point and stayed at n data rather than going up to n squared? Okay, and that would have been basically making a decision previously. Now, even more here, it's probably obvious, we never needed to create those lists at all. We could always have just addressed the mean to the list slice. We could just have used those indices. But we did it this way because this is, again, an illustration. So never mind that, we really didn't need those lists. Think about the data sense in which we didn't need those lists. We didn't need the lists, we needed their mean. So when we're thinking like that, we're seeing that far more, there is a couple of chunks of this task. There's the creating the list of our paces, There's the working out the means of all the subsections, and then there's the relating those two things. And that is probably a better way to write this code. So let's have a look at what I really would write for this code instead of the slightly mad version. Okay, so once again, we've got the same gist. This is all the same as you saw before. Now I've named this function a little better because it's create list and check subsections. Is that a great function name? No, but it's not bad. It's telling me that in some sense it's creating a list of something and it's doing some checks on some subsections of that list, and I can probably infer that n is usually a number of points, and my comment upstream reinforces that. And the fact that I've used subsections and this subdistance is implying that that's in somehow related to the size of subsection, the position of something to do with the subsection. It's a passable function name, and again, this function does come down a bit to do the thing. So let's go look at it. It's not at the top because now we have some functions. Here it is, create list and check subsections. Okay, it's got a comment, good start. Create a list of instantaneous paces of length n, check that each one has a contiguous, contiguous sublist of fractional length subdist, such that the average of the sublist is greater than or equal to the average of the whole list. Well, that tells us what's happening. Doesn't have any relation to our question, as in that's talking about what it's physically doing to the list, not what they might represent to us. But it's a pretty good comment. And in fact, in the context of this function, it doesn't care that we're thinking about race paces. All it knows is what it's doing to the data list. And then we have its body. Well, that appears to be creating a list somehow. It's using that n variable again, so it's probably got something to do with that number. That's getting the average of whatever we just created. That's doing something to do with those sublists, we can infer, calculating the sublist paces. As it turns out, we'll see in a minute, that's calculating the means of each one, giving us back a list of them. This is doing the check of the sub relative to the average. Once again, I've made a mistake there with respect to my speaking. That should have been greater than or equal. That's a bit of debug code that I might want to have in. Again, this version is a lot easier to debug. And this is asking the final question. So this is saying, create the list of true-false values for that condition. Is the item here greater than or equal to the average? And this is just saying, was at least one of them true? Same question, same problem, rather better code. And we can just go back and check. Yep, so this is the filling in, create and fill a list of length n with numbers between 0 and 1. This breaking into functions has given us a much easier way to write comments. And then we can just substitute the body of that comment for where we see this function used. So we create a list, we add random numbers to it, we return it. In this case, for a given list, generate all contiguous sublists of length blah and calculate their averages. Now that comment is coming back to my philosophical question. It could not, it doesn't matter much. In general, you're better not to. You're better to keep the thing talking about just what the code is doing, not what it might mean for the rest of the code. Otherwise, if I were to change what I was using this function to do, I would have to change my comments. I might forget to do that. Similarly, my variable namings here aren't great. I should perhaps have been thinking more in terms of the lists, not this concept of those being representing a pace, a running pace. Anyway, I find out the length of my list. I work out, just as before, the size of my subsections. I work out the number of subsections that I therefore have. And I calculate the mean of each subsection, and then I return that list of means. So, I've got a few things here. The comments are easier. The function names are half decent, if not great. Several variables have reduced in their scope. For instance, these two, they're relevant only for this section of our code. They're not relevant after that. So it's nice to be able to limit their scope and know that they don't have any use in other places in the code. That's kind of, people say global variables are bad. Well, variables that have too big a scope share a lot of the pathologies of a global variable. You don't know where they might be modified, you don't know if they'll be used later. If you insert a modification into a variable like this, if you insert a line into your code that modifies a variable, are you sure that you've accounted for all of the changes that might make to the code? And the smaller the scope of a variable, the more sure you can be of that question. Now, functions are really good at letting us limit the scope. These variables exist only temporarily, they're gone afterwards. Many languages actually let you do block-wise scoping, where you can just say, oh, let this variable exist only for this long. Python doesn't have block scoping, but if you've used the with word, so with open file as my file, that's doing the same thing. My file exists only for that block. It's kind of block scoping. And the other thing is, our doing work function has now come down to a much smaller sequence of steps. In fact, if we believe all that stuff about how people can only think about 7 things at once, we're now at 5, which is a good bit shorter than we were before, where we had to somehow... It is not that we couldn't make the same inferences, but in this case the functions are doing work for us that otherwise we would have to do by making mental notes of what the code was doing as we went along. And the last kind of thing is we could go further than this. This variable, for instance, it's not required. I don't need to actually make that. I've been talking about, keeping data, making data bigger than it needs to be. I never needed to create this list of flags. I could just have done the same thing I did before with the skipping straight to the true-false answer. However, what this lets me do is have the, just have a bit more mental space, because I've done 2 steps instead of 1. So if I wasn't in Python, I probably wouldn't have created this as a list like this. I'd probably have done a loop, and I'd have put any debugging information I wanted in the loop. But because Python list comprehensions are so commonplace, I do it like this, where I make the list and then I can look at the list and analyze it if I want, or I can return the answer based on it. So in a sense, I've allowed some excess data, but I think it improves the clarity. So what's the point? Nobody has managed to give a good description of what a single purpose means for a function. It's probably impossible to do so. But if you've got something like this that's a kind of data analyzer program, then you can think about the flow of data as a analog, as what you want your I'll try that again. You can use the flow of data to help you break your problem up into subtasks, because you can say which parts need which data. Do they group together? Can I therefore restrict that data to just a subsection? And if you can, maybe that's a function. Maybe all of the stuff that needs this bit of data can be put together into one function, or maybe I can split things up. The data flow can be a good way of breaking your task up. And in particular, think about sort of making decisions as you go. It's basically what you're looking for here is reduction operations. They reduce the amount of data, rather than keeping it all around and just doing tests on it. You produce a new piece of data that represents the answer to a previous question. So like this line, it's a good illustration. It is changing from a list of numbers and this average pace number into just a list of true-false values. It is a reduction. It's not a very powerful one because it's only removing one item from our data set, but it does mean we need one less piece of data now. We don't need each of the paces and the average, we just have the answer to were they better than the average. The reduction operations are the second half of any data processing code, the bit where you go from the data to the answer. But it is rarely the right thing to do to have a code be make all the data, do all the reductions, done. You want to interleave those things in such a way that the program as a whole becomes a logical thing, makes sense, is easier to understand, and so on. You can have functions that make decisions rather than just give you back data. So that's kind of it. It's a bit of a mixed thing, covering sort of everything, but ultimately, question, how do you write a good function? Answer, I don't know. Do lots of things that help you write good functions and hope, I think, but concentrate on having them do one thing. Think about what a thing can be. It is context dependent. It's not easy, but if you come back to some code and you look at the function name and you go, oh, okay, I understand that, it was probably a good function name. So this code is going to be on the GitHub. Again, I am not saying it's good code, it's not commented, it's not very Pythonic, it's just something I knocked up because I actually really wanted to know the answer to this question. We will be back maybe next week, and thanks for listening.